All right, let's get started here. And for the moment, we are still discussing about how to optimize an initial database schema. The last time we have been introducing normal forms, and the normal form essentially just means if a schema is in a normal form, it means that it has certain desirable formal properties. For instance, in particular, it avoids redundancy. And the last time we have been discussing about two of the most popular normal forms that are used heavily in practice. One of them is the Boyce-Codd normal form, which you see here. We essentially test whether a schema is in Boyce-Codd normal form by considering all functional dependencies, which means the ones that are initially given as well as new functional dependencies that we can infer from them. And for each functional dependency that holds on a single table, we test and make sure that one of those two conditions here is satisfied. Either the functional dependency is trivial, meaning that the right-hand side is included in the left-hand side, or the functional dependency is a key constraint, which means that the left-hand side implies all attributes in the entire table. Because if any of those two conditions is satisfied, it means that we don't have any problems related to redundancy. So this is the Boyce-Codd normal form. It is quite restrictive. If none of those two conditions is satisfied for at least one functional dependency for at least one table, then Boyce-Codd normal form does not hold. We have seen a slightly more permissive normal form, which is the third normal form. And it is slightly more permissive compared to Boyce-Codd normal form because here we allow one additional case, which is the third one in this slide. We also consider functional dependency as okay if the right-hand side is part of some minimal key of that relation. And the minimum key, it is essentially a set of attributes which imply all attributes in that table. But if you remove any of those attributes, then you do not have a key anymore. That is why the key is minimal. So the third normal form is a little bit more permissive. And the reason why we want to be a little bit more permissive is that the third normal form can always be achieved by preserving dependencies. Dependencies, those are essentially those functional dependencies. And if I want to verify that those functional dependencies are satisfied as integrity constraints, if I have a dependency preserving normal form, it means that in order to verify all relevant dependencies, I only have to consider single tables, but I don't have to start joining tables in order to verify anything, because that would be expensive. So those are two different trade-offs between how much redundancy we are willing to accept and how efficient checking constraints can be and whether it requires joins or not. So those are the two normal forms that we have seen. And we have also quickly started to discuss about how we can get to any of those normal forms last time. The key technique in order to get to one of those normal forms, that is decomposition. Because those normal forms, they only require that conditions are satisfied for functional dependencies that hold within the same table. So if we keep decomposing those tables, then we have to worry about less and less functional dependencies. We want to be careful when decomposing those tables because we want to decompose them in a way such that we can still reconstruct the original data. This is what we call a lossless decomposition. And here we have essentially the condition for lossless decomposition. If I have a relation R, which is at the same time like a set of attributes, and now I decompose R into two relations X and Y, where X and Y are essentially the attribute sets of the new relations. And in order for this decomposition to be lossless, I must guarantee that if I do a natural join between x and y, then I get back the original content of the relation R. And that is the case if one of the two conditions on the bottom of the slide is satisfied. If when intersecting x and y, I get something that implies x, then I'm okay. Or if by intersecting x and y, I get something that implies y, then I'm also okay. What this means essentially is that if you only take the join columns of the natural join, then you get a key for one of the two decomposed relations, x or y. And that means that one row on one side matches with exactly one row on the other side. And in that case, you know that you will get the original relation back if you join those two decomposed relations by a natural join. So I'm going over this relatively quickly. It's a reminder. Those are things that we have discussed in a little bit more detail last time. Now we have also made a little example for a lossless decomposition. I'm not going to go into it in too much detail, but I encourage you to have another look at this example. So here we have decomposed the things in a way that we can reconstruct the original relation by a natural join like this. And here we have decomposed things in a different way, which does not allow us to reconstruct the original relation. Here, if we do the join, and we get something which is actually larger than the original relation because it contains more rows. And that means that we have lost information about which TA in this case is associated with what office. So we can use decomposition in order to come to a normal form. This is how we get to the Boyce-Codd normal form. The algorithm is relatively short. Essentially what we do is that we keep decomposing tables until we get to Boyce-Codd normal form. Whenever we want to check whether something is in Boyce-Codd normal form, then we iterate over functional dependencies and check whether they hold for specific tables. And if we find one functional dependency of the form A implies B, where A is an attribute set and B is a single attribute, and if we find this to violate the rules of Boyce-Codd normal form, then we decompose the corresponding relation R, as you see here. We decompose it into two new relations. The first one has essentially the same attributes as R, just that we take out B. And the second relation that we achieve by the decomposition, it includes the attributes in A and additionally B. So this is the rule for a decomposition. And we know, first of all, that this decomposition will be lossless, because if you do the math, if you intersect those two relations after decomposition, if you intersect R minus B and AB, then in the end we get A. And as we know, that implies B. Therefore, by intersecting the two decomposed relations, you obtain a key for the second relation, which is AB. So here we know if we apply this rule, then the decomposition must be lossless. So that is the first desired property of the algorithm. Now we could wonder whether this algorithm will ever terminate. It will, because whenever you decompose a table, it gets smaller. At some point, you must end up with atomic tables, basically. And also, since we decompose whenever a functional dependency violates Boyce-Codd normal form, and after this decomposition, you see that the functional dependency that caused the problem does not apply to any of the decomposed tables anymore. So this decomposition essentially fixes the problem. And once we terminate and do not decompose anymore, we therefore know that we must be in Boyce-Codd normal form. Otherwise, we would continue decomposing. One remark about this, the end result might actually depend on the order in which you consider your functional dependencies. So in the following, if we make examples about how we get into Boyce-Codd normal form, for instance, please keep in mind that multiple solutions to those examples are generally valid. It depends on how you order the functional dependencies. In the end, all that matters is that we are in Boyce-Codd normal form. So for a given start schema, we could have multiple equivalent schemata that are in Boyce-Codd normal form. All right, so this is the algorithm for Boyce-Codd normal form. You essentially just keep decomposing using this rule until finally no function dependencies violate the rules of Boyce-Codd normal form anymore. Is there any questions on this? All right, good. So then let's make a little example. You can also find this example in the book. Here we have given a schema simply as a collection of attributes. We assume that we have one relation which includes columns called CSJDPQV. So I'm not gonna go into detail with regards to the semantics of those columns. For the example, it doesn't matter. If you're curious, in the book, you'll find more details. This essentially refers to a scenario where we store information about a project. For the example, you only need to know which attributes are contained in the relation. You have given that attribute C is a key for this relation, so it implies all the other attributes in this relation, and the attributes J and P together imply C, attributes S, D together imply P, and J implies S. So as a little exercise, I invite you to try bringing this into Boyce-Codd normal form. I give you a few minutes. Use the decomposition method that we have just seen. And while you are looking into this, I'm going to have a look into the chat because there might be some questions. Okay, very good question and reply. The question was where we get the initial functional dependencies from, whether it's the full closure or whether it is some kind of attribute closure. So in general, you need to consider the full set of functional dependencies, and that includes the ones that you can infer from the original functional dependencies. So typically, it is not necessary to think about all possible functional dependencies, but in a given scenario, when looking at the tables and trying to decide whether you need to decompose them further, then you can sometimes apply actually attribute closure in order to find out whether specific functional dependencies are relevant to you. But conceptually, you have to consider all functional dependencies that can be inferred from the original ones. So if you're given a set of functional dependencies, it's not the full set of functional dependencies that holds, but you might also have to infer new functional dependencies from them. Right, I give you another minute. So even if that might not be enough time to fully finish the example, at least have a look and think about how you would get started with this. Any more questions on the material that we have covered so far? All right, let's have a look at the solution here. So we have given this schema and, and we have given constraints. So first of all, looking at those function dependencies that are even immediately given, you already see that some of them violate the Boyce-Codd normal form constraints here. So a first function dependency is SD implies P. And so first of all, this is not a trivial function dependency because the right-hand side is not simply a subset of the left-hand side. Also, SD does not seem to be a key. We can infer P from it, but after that, it doesn't propagate further. So here we have something which is neither a trivial function dependency, nor is it a key. And this is why it violates the constraints of Boyce-Codd normal form, and we have to decompose. So here we decompose into two relations. So first of all, we have to take out the left-hand side of the function dependency from the original relation. Then we get one of the two relations after decomposition, or precisely we get the attributes that must be included into that relation. And also we have a second relation which simply combines all the attributes from the function dependency, S, and P. So here you see the two resulting relations after the decomposition. So in the original schema, we had one relation. Now we have decomposed it. And so we have replaced it by two relations. And yes, very good question. So the next functional, so one function dependency that we don't have to worry about, for instance, that is JP implies a C because C is a key. And that means via transitivity, JP is also a key. So yes, going through all of those functional dependencies, we have given that C is a key. So that is nothing to worry about. We have that JP implies a C, so JP is also a key, so nothing to worry about. We have just taken care of SD implies P, and then we also have a J implies a S, and that one would also be problematic. So after the decomposition, we essentially go through all of the functional dependencies again, and now we have taken care of the first few, but the last one, J implies S, this one is still not okay. This is why we decompose things further. So in one resulting table, we have simply the attributes from the function dependency causing problems, which is J and S. And in the other part of the relation, we have the attributes from the relation that we are decomposing minus the left-hand side. So here, after the first decomposition, we end up with two relations, SCP and CSJDQV. And here, when comparing against the functional dependencies, maybe I make that in a little bit more detail. So when comparing, when analyzing SDP, that relation, then there is only one functional dependency that has its attributes only from that relation, and that is SD implies a P, but this one is a key for this relation. For the right functional dependencies, we have that C must still be a key. JP implies C. That one does not have the attributes only in the second relation. And J implies S. That one still has all attributes in that second relation, and it is not a key, and therefore we need to decompose the second relation further. And this is what we are doing here in this step. We are decomposing it into the two relations JS and chat and CJDQV. And after that, we have obtained three relations by two decompositions. And if we compare them against the functional dependencies, we find that all of them are either a key or they don't apply to attributes of one single relation. And this is why the resulting schema is in Boyce-Codd normal form. All right, so this is a relatively small example. Also note that we could have gotten to a different Boyce-Codd normal form if we had started initially by considering the functional dependencies. J implies S. But in the end, all that matters is that we get to some Boyce-Codd normal form. And if we keep decomposing, then that will happen. All right. Good. Any questions on this? All right. Good. So one thing that Boyce-Codd normal form cannot guarantee is that we preserve all dependencies. So dependency preservation, I've already quickly mentioned what it is intuitively. So here you have a little bit more details. So in general, assume that we decompose a relation R into relations X and Y, where those letters essentially designate the attributes of the corresponding relations. And now assume that we verify functional dependencies only on the relations X and Y separately. So we enforce all functional dependencies that can only be checked by using attributes from X, and we check all functional dependencies that can be verified using only attributes from Y. And if by enforcing those functional dependencies on a separate relations, we have implicitly enforced all functional dependencies that held initially, then we say that the decomposition was a dependency preserving. I believe there might have been a question. Okay, yes, very good question. So in a way, the point is to break up dependencies that violate constraints that don't comply with the constraints of Boyce-Codd normal form. And you are absolutely correct that dependency preservation is somehow at odds with trying to decompose things as much as necessary in order to avoid any redundancy. So that is totally the right insight here. And that is exactly the reason why people are willing to relax the constraints of Boyce-Codd normal form, because it is indeed sometimes at odds with dependency preservation. So a third normal form is kind of a compromise where you decompose as much as possible without running into dependency preservation problems. So dependency preservation still allows you to break up some inferred functional dependencies, as long as you can still verify enough functional dependencies on the two resulting relations. But you're absolutely correct that it is at odds with trying to decompose as much as necessary to avoid redundancy. That is the compromise. Boyce-Codd normal form does not guarantee dependency preservation. The third normal form that we have seen does. And in the following, we're going to see an algorithm which allows you to get into third normal form by preserving dependencies. Yes, so that is totally the right insight here. All right, and here a little summary which connects to what I was just saying. So we have seen two properties for decompositions. We have them lossless, and we can have them dependency preserving. Those two properties, by the way, are independent from each other, so none of them implies the other one. Boyce-Codd normal form may lose dependency preservation, while it, on the other side, removes any redundancy. The third normal form preserves dependency preservation. It preserves dependencies, and under that constraint, it tries to get rid of as much redundancy as possible, basically. And all of those normal forms, they only use lossless decomposition, so you can achieve them using only lossless decompositions. So in the end, you're not losing any data. But that is the compromise of third normal form. It might still allow some redundancy, but in exchange, it allows you to preserve dependencies. This is how we get into a third normal form. So here we essentially do something quite similar to the process for Boyce-Codd normal form. The only difference is that in order to preserve dependencies, we might actually choose to add new relations. So whenever we have a dependency of type A implies B, which is broken by the decomposition, then we simply add a relation A implies B into our database schema. In order to make this work well, it is important that we use the right set of functional dependencies for our analysis. We have to use something called a minimal cover of functional dependencies, which essentially means that on the right-hand side of each functional dependency, we only have a single attribute. And if we delete any functional dependency from our set, it changes the closure, meaning the set of functional dependencies that can be inferred. Also, if deleting any attribute from any functional dependencies left-hand side, it will also change the closure. So this is essentially a set of functional dependencies where every functional dependency and every attribute is necessary. And if we have computed that, then we can use it in order to decide which relations we want to add during the decomposition. So we are not going to go into detail in terms of how we calculate, for instance, the minimum cover. This is, if you're curious, there's an algorithm given in the database book. But on a high level, this is how we achieve a third normal form. So the only difference to Boyce-Codd normal form is that we might decide to add, so to speak, not really redundant, but we might decide to add additional relations that contain attributes that also appear in other relations. And after we have added them, they allow us to check certain functional dependencies without breaking them. So here we simply add new relations which allow us to verify functional dependencies without having to do any joins. And by broken, I mean that both of the, basically in order to verify the function dependency, you would have to include attributes from different relations, unless you add the new relation, which contains all the specific attributes you're interested in. In that case, you can just verify using the data from the new relation and you don't have to do any joins. So broken means like attributes from a function dependency that used to be in the same relation. After the decomposition, they are now in different relations. So in order to verify that the function dependency holds for all data, you would have to essentially join them together, unless you add a new relation which contains all that data in one relation. And this is what a third normal form is doing. Any other questions on this? All right. So we are now concluding the chapter on a database design. I want to conclude it with a little example. I wanted to do the entire process starting from designing the database and finishing with optimizing the database schema. So let's make a little example. The first step after analyzing use cases is to typically draw an entity relationship diagram in order to get a sense for what information you want to store in the database. So for the moment, let's assume that we want to design the database for a web shop, and this is a relatively small web shop apparently, which can be summarized by this description over here. We have accounts with a unique name and the password and a timestamp of the last login. Customers of the web shop, they own at most one account. They have a unique customer ID, a name, and one or multiple addresses. And each address has an address ID, a street name and number, and an associated country. And then finally, we store information about employees, which have a unique employee ID, a name, one primary address, and at least one assigned account that they need to supervise. They also are associated with a job title, with the number of hours that they work per week, and with a salary. So for this scenario, I give you a few minutes in order to draw an entity relationship diagram, and I'm happy to answer questions here on the chat. In the following steps, we're gonna translate this entity relationship diagram into a relation schema, and then we're gonna optimize the relation schema. So by the small example, we're gonna do all of those steps that we have seen. Any questions on entity relationship diagrams, or perhaps on the course material covered after that? Okay, and there's a question about the semantics of bold lines. So bold lines indicate a participation constraint, which means that one entity needs to be in a relation with at least one other entity or combination of entities. So the at most one constraint would be expressed by an arrow. Any other questions about entity relationship diagrams? And there's another question about whether the account supervision is associated with the properties listed or the employees. So the account supervision would would associate the employees with the accounts. So yes, so that would, I mean, here I would probably represent it as one entity connecting to another entity, employees to accounts. So in general, we connect entities together. There's also aggregation, which essentially connects a relationship to an entity, for instance. Right. But please let me know in case I'm misunderstanding the question. All right, let's have a look at the solution. There's multiple possibilities, so this is only one of them. But what we're doing here is that we introduce entity types for accounts, employees, customers, and the address. They have the properties that are mentioned on the previous slide. Always important to mark up which of those properties have unique values. They are underlined in this representation. And we do have relationships connecting those entities. And there was already the question about constraints, and that applies here because in the description, you have given some information about whether one or multiple entities of a certain type can be connected to other entities, or whether we need to have at least one entity in a relationship. So here we see, for instance, that customers have at least one address, one or multiple addresses, and that is expressed by the bold line connecting customer to the corresponding relationship symbol. And also customers, they own at most one account that is expressed by this arrow. As the employees have exactly one primary address, we have the combination of the two, a participation and at most one constraint. So, and here the supervision is connecting the accounts to the employees. All right. So this is one possibility to represent this scenario. So in the following, we try to translate this into a relation schema. I'm giving you this entity relationship diagram, and let's give it a couple of minutes, try to translate at least a part of this entity relationship diagram into a database schema. And by doing this, also take into account the nature of the constraints on those relationships, because sometimes that allows you to obtain a more efficient representation with less tables than when applying generic methods. And if there's any questions, then please put them into the chat. Okay, and while I let you translate, I'm answering questions here. Whether we could have two different relationships rather than one has. So there's two has the relationships. Admittedly, the naming could be a little bit more expressive here, but which of them do you mean? Oh, yes, absolutely. Yeah, frankly, the naming here is not particularly creative. You should ideally use more expressive names than what I did here. Yes, you absolutely can call them differently. The name should reflect whatever the semantics of the relationship is. So here, has fits for both, but probably you could use something else. And just because they have the same name, by the way, it does not mean that it is the same relationship, basically. So whenever you have one of those diamond symbols, then that's a separate set of relationships that is represented there. And here, even if two of them have the same name, then nevertheless, they represent different types of a relationship. And you're absolutely right that you can and probably should name them to something a little bit more expressive. But it is allowed to have multiple relationships that have the same name. Yeah, good question. Any other questions on this? All right, let's have a look at one possible solution here. And so what we're doing here, there's a couple of standard cases, so to speak. Here, first of all, we have, for instance, the employee relation, which simply contains the attributes associated with the properties that we saw in the entity relationship diagram, and even the representation for keys is the same here. So the employee ID is unique, so we underline it also in the relation schema. Similarly for the address, here we just use the attributes that we have seen. For instance, for the supervisors relationship here, we can simply connect the employees to the customers. And here I should perhaps first say something about how customers and accounts are represented, because supervision that according to the initial description actually links an employee to an account. But we have this connection between accounts and customers that you see here. And one customer can own at most one account. So in this case, we know that the customers, essentially, we can essentially merge customers and accounts into the same relation. So if accounts are always associated with a customer, then here we can simply essentially merge the attributes from customers and accounts together. So we have the customer ID, this is the customer ID, the customer name, the account name, the timestamp, and the password. So if we merge them together, this is why we can refer directly to the customer ID in the supervisor's relationship. Okay, and here there's a great question. How do we know that customer implies account, customer to account is a one-to-one relationship? And what happens if an account is owned by more than one customer? Okay, so that is a valid question. So here one should probably represent that as additional constraint in the entity relationship diagram. So here, okay, I guess in a way we have also used some domain knowledge for stating that an account is only associated with one customer. But yes, if an account could be associated with multiple customers, then you're perfectly right. We couldn't merge them together like this. So yes, strictly speaking, that would require some additional justification. Yeah. All right, so here we assume basically that it is a one-to-one mapping, and that there might still be customers without an account. That is okay. But if there's an account, then it is only owned by one customer. And if we make that assumption, then we can represent, for instance, the supervisor's relationship by connecting employee IDs to customer IDs directly. The final relationship that we need to discuss is the one between customers and addresses. And here we are simply linking the customer ID to the address ID. So that is one possibility to represent that, but there would also be other ways. I just wanted to show some ways in which those, in particular, in which those constraints can be translated into corresponding relations. And one employee has multiple addresses. What would happen in that case? So here we have said that one employee has one primary address. So if we would have multiple addresses per employee, then that would be represented as a separate relationship. So here we would just introduce one new relation, which is something called employee has address, and then it contains the employee IDs and the address IDs. So yes, if we could have multiple addresses per employee, then we had to introduce a new relation in order to represent that. Yeah. All right. So now Last point, let's try to bring that into Boyce-Codd normal form. I give you the schema here. So here you are not given any functional dependencies yet, so you might have to consider the scenario, and you have to verify whether those functional dependencies hold. We're already approaching our time limit, so I give you a few seconds to think about it, and then I'm gonna show you the solution. Just perhaps think about how you would approach that and which steps you would need to take in order to get to Boyce-Codd normal form. All right, I think we have to wrap it up here. But the way to get to a Boyce-Codd normal form, or to verify first of all whether the initial schema might already be in Boyce-Codd normal form, that first of all needs over functional dependencies. So in this description of the scenario, we have a lot of functional dependencies, or a few functional dependencies given. So there's a couple of key constraints. And here perhaps we can assume that if somebody works in the same job and the same number of hours, then the salary will always be the same. So if we impose that, then we get one constraint which violates the conditions for Boyce-Codd normal form in the employee table, where so far we have stored the job hours and the salary. So in that case, we would have to decompose the employee table into two tables, where in the first one, we using the decomposition rule that we have seen, we would just take out the right-hand side attribute. So we would essentially have the employee table without the salary. And then we would introduce a new second relation that includes all the attributes that appear in the functional dependency, which is job hours and salary. And we could name it something like job hours to salary, for instance. And now we have decomposed the relation, and thereby we avoid redundancy, and we get into something which complies with the constraints of Boyce-Codd normal form. So this is one simple example that illustrates the entire process. We start with an entity relationship diagram, then we translate it into relations, exploiting our knowledge about the specifics of the domain. Then we try to optimize the initial schema by using functional dependencies, which also come from our domain knowledge, or which can be inferred from combinations of other functional dependencies. And finally, we typically want to decompose the schema into, for instance, Boyce-Codd normal form, which is quite restrictive. And after that, we have a database schema that avoids redundancy. So this essentially concludes the chapter on a database design. We have seen how to draw entity relationship diagrams, how to translate them into schemata, and how to normalize the resulting schemata. The next time we will start discussing about database systems which expand traditional database systems in one way or the other, starting with distributed database management systems. I wish you a nice weekend, and then I see you next week.